Hello friends, welcome to MATLAB school. In this video, we are going to see the simulation of PMSM powered electric vehicle with drive cycle and driver model. Let us get into the simulation. The same model is available for download from the link given in the description. If you want, you can download it and you can use it for your purpose. So this is the simulation model. So here we are going to simulate the electric vehicle which is powered by PMSM motor. So for this electric vehicle, we need to give a few things like the drive cycle. Drive cycle happens to be the reference speed of the vehicle. So here the reference speed is coming from the drive cycle. So here we have a number of drive cycles like WLTP, NEDC. So like that we have different types of drive cycles. So I have chosen the Japanese 10 mode drive cycle. It runs around 135. It will take 135 seconds to complete the simulation. Okay. So let me give the outline of this simulation model. This is the lithium ion battery. I have chosen 300 volts and 100 Ah capacity. The SOC of the battery is 50. And here we have the universal bridge. In this universal bridge, I have chosen the number of bridge arms to be 3. And the power electronic device is IGBT and diode. And this is the PMSM model that we have. In the PMSM model, I have chosen mechanical rotational port as the input. In older versions of MATLAB, we will see only torque and speed as mechanical input, but in the latest versions of MATLAB, we have mechanical rotational ports in addition with torque and speed. So with this addition, we can easily include the physical models like the torque sensors, vehicle body. So here we have the vehicle body and these are the wheels and this is the breakdown. So let us discuss one by one. Here we are using FOC to control the PMSM motor. So here we have the FOC controller. So before that, let me explain what driver model is. Longitudinal driver is the driver model that we have here. So this driver model gets the input from the previous stage. So previous stage happens to be the drive cycle. So the output of a drive cycle will be in terms of meter per second. If you want in kilometer per hour, we have to just change this to kilometer per hour. So I have kept it as meter per second. So the output of this drive cycle is given as input to the longitudinal driver model. To this driver model, we will be giving two inputs. One is the reference speed and second one is the feedback velocity. Feedback velocity is the actual speed of the vehicle. So as you can see, it is coming from the vehicle speed. Okay. Right. So here we have the driver model. This driver model will control the vehicle's speed. Also, it will apply brake based on the requirement. Okay. So this will be the reference speed, and based on that reference speed, it will make the vehicle. This longitudinal driver will make the vehicle to run at the reference speed. So I have put grade as 0. So if you want to include the inclination of the particular road, you can include some values for grade as well. The acceleration command and deceleration command will be in between 0 and 1. So with respect to our requirement, we need to multiply the values from 0 to 1 to, with some other values. Okay. So here I have multiplied the output of acceleration command with 500. So the values that we get from the acceleration command, as I told you earlier, it will be in between 0 and 1. So this 0 and 1 will be multiplied, the values in between 0 and 1 will be multiplied by 5000. So ultimately we'll be getting the product of this acceleration command with this 500. Okay, so that becomes the reference current, reference quadrature current. So this reference quadrature current is compared with the actual quadrature current. So this actual quadrature current is calculated from here. Okay, so the phase currents are sensed. The sensed phase current will be connected to class transform. So this class transform will convert three-phase AC signal to two-phase AC current. Okay, so this again, this two-phase AC current will be converted to a direct axis and quadrature axis currents. This direct axis and quadrature axis currents will be like a DC signal. So we can use PI controller only if you use DC current. See, comparing two AC signals is not possible. To connect PI controller or some other controller, always we will be preferring the steady state parameter. So here we are converting the phase currents to two-phase AC currents. Again, the two-phase AC currents is converted to direct axis and quadrature axis current. So this is the actual direct axis current, and this is the actual quadrature axis current. So with the reference quadrature axis current, we are comparing the actual quadrature axis current. We are comparing these two currents, and finally we are finding out the error. So this error is given as input to the PID controller. So this PID controller will produce the output. That output is the reference voltage, reference quadrature axis voltage, and parallel to that we have zero value for direct axis reference. This zero value will be compared with the actual direct axis current. So an error will be generated. The error is given as input to the PID controller. So output of this PID will be the direct axis voltage. Okay. So again we are going for path to class transformation. This transformation will convert direct axis and quadrature axis currents of voltages to alpha beta voltage. Again, this inverse class transformation will convert alpha beta to three-phase AC voltages. Then we have a PWM generator that will generate pulses for all the 6 switches. Okay. So this the gates produced by the previous stage of the simulation will be given to the universal bridge. So inside this universal bridge, as you know, there will be 6 different switches for converting a DC signal, DC voltage to AC voltage. So based on the gate signals produced by the FOC controller, the gates will be produced. Okay. Now coming to the load side. At the load side, we have connected the transmission system. This transmission system is connected to the vehicle model. So here inside the transmission system, we have the gear arrangement. Okay, it is taking a while to open. So this is a gear arrangement. In this gear arrangement, there will be there will be two teeth actually. The ratio is 3. It's just like a regular gear that we find in vehicle. So both the gears will have its own inertia. So we are including inertia for both the gears. So the torque produced by the the load torque. Actually, it's the load torque which is connected to the motor. So this load torque has to be measured. So to measuring the load torque, we are having an ideal torque sensor. So this torque sensor will measure the load torque. So this function, this is the solver. This solver is similar to the power GUI block that we have in the regular simulation model. So only if you connect this solver, the simulation will work. Otherwise, the physical model of MATLAB won't work. Okay. So the next stage is the vehicle model. See, in the vehicle model, we are getting the output. We are getting the power from the vehicle. Power from the motor. It is connected to the wheels. So here we have the vehicle body. The parameters of the vehicle body. Okay. Yes. So these are the parameters that we feed in. The mass of the vehicle is 1500. Number of axles, number of wheels per axle is 2. And we are giving few more details which are relevant to the mechanical engineering. Okay. So this is the vehicle model, and to the vehicle body we'll be connecting 4 wheels. So this is the left rear wheel, this is the right rear wheel, this is left front wheel, and this is the right front wheel. So this is the connection which represents the ideal connection between the vehicle body and the wheels. And here we have another one connection called H that represents the feedback from the wheels to the vehicle body. So here we have the brake. This brake shoe will be, it will be connected to the driver model's brake. So the deceleration command will make the braking of the vehicle. So whenever we want to decrease the speed or decelerate the speed of the vehicle, this brake will be applied. So let us get into the simulation. Let us run the model. Since it is, it will take 135 seconds. We need to wait for a while. So here in the scope you can see the line voltage between phase A and B. Then we can see the reference speed and the obtained speed. And the third scope will give you the torque produced by the motor. And here we can measure the battery parameters like SOC of the battery, current, also the voltage of the battery. So there will be some gap, initially gap in the sense the vehicle speed has to be maintained at 0 initially as per the drive cycle. So we can open the SOC of the battery, battery's parameters. Okay, we have two scopes here. So the first scope, uh, here we have a SOC, current and voltage. Then we have line voltage, vehicle speed and torque. The torque will be in terms of Newton meter. So it will take a while uh, for the vehicle to start. Yes, the vehicle has started to move. Yes, here there are two graphs. The red one, I mean the yellow one is the reference speed and blue one is the actual speed. So as you can see, the vehicle is keenly tracking the reference speed. So this is the torque produced by the motor. Yes, I think the vehicle is reaching a flat surface. So it's a flat speed profile. Okay, so it will take 135 seconds for the simulation to complete. So I'm passing now, and we shall remove, we shall resume the thing after a few seconds. Yes, the simulation has completed 50 seconds now. So let us wait for 135th second. So this is the SOC. So as you can see, when the vehicle reaches a steady state, or when the vehicle speed reaches zero, you can see the SOC remaining constant. And here the braking will be applied. Okay, let us see the brake force and the load torque. So this is the load torque, and this is the corresponding torque produced by the motor. And this is the brake force. Okay, so as you know, the brake is applied here around 42 seconds, 40 to 45 seconds. So the brake is applied here. So as you can see, the brake force is varied with respect to the amount of braking that we need. As you can see, the vehicle speed is increasing again. So the vehicle is accelerating now. So as per this profile, the speed will reach, and at some point in time it will reach a flat speed profile, then the speed will decrease. At this time you can see the braking. Again there is a slight increase in acceleration, and then there is a steep braking. So we shall expect the same speed profile from the vehicle. So let us wait. So let me open the brake force as well, so that we can get a very good idea about the response of the braking system in the vehicle. So in a while the vehicle speed will reach the flat profile. So I think it has reached the flat speed profile. Okay. After some time there will be a braking as per the speed profile. Yes. Now there is some braking happening. Yes. As you can see, the speed of the vehicle is getting reduced. Simultaneously, you can see the brake getting applied by the driver model. Yes, as per the speed profile, the speed will decrease, then after some time it will increase again. Yes, as you can see, the simulation has completed now. So here also we can see the speed profile. Here there is a increase in acceleration, then there is a deceleration. Again the slope of deceleration is decreased further, so we need to have improved braking there. So as per the requirement, here we have a higher value of braking. So this is the SOC of the battery, and this is the SOC of, I mean the current of the battery, and this is the voltage. Okay, the same model is available for download in the link given in the description. You can download it and you can use it for your purpose. Please subscribe our channel. Also, you can share the channel to your friends. Please hit the like button. Also, you please click the bell button. Then only you will receive the notification whenever we publish a new video. Thanks for watching. Thank you.